this session, I like to explain what a first-order ordinary differential equation or ODE is and why it's important. Basically, a first-order ODE is used to describe things that change over time, like temperature, cooling down, how fast a disease spreads, or how money grows in savings. It works by linking a value with how fast that value is changing. These equations are useful in many areas like physics, where they are used in motion and heat problems, in engineering for circuit and fluid flow, or in biology to model population growth. What's powerful about first order ODEs is that once we solve them, we can actually make prediction. So not only do we understand how something works, but we can also plan ahead based on that. That's why learning how to apply this equation is so useful, not just in math class, but also in solving real-world problems.
Good day everyone. Today I will be presenting the Pbl table based on the study of radioactive decay. We begin with the facts. The substance we are analyzing undergoes exponential decay, starting with an initial mass of 80 grams and after 10 years, the remaining mass is 50 grams. The decay process follows an exponential model, and this concept is widely used in fields like nuclear science, medicine, and environmental studies. Now let's move on to the ideas. We use the exponential decay formula. Mt equals to m0 times e to the power of negative kt. By plugging values into the formula, we can model the mass of substance over time. Once we determine the decay constant k, we can estimate the remaining mass at any time, for example, after 25 years. Also, we can predict when the mass will drop below a certain threshold, such as 10 grams. This is useful for understanding half-life and decay behavior. Next, we look at the learning issues. One challenge is learning how to derive the decay constant k from the given data. Another is knowing how to apply logarithms to solve for both k and t. It's also important to understand the concept of half-life, how exponential functions behave, and how to solve inequalities involving them. Lastly, we address the action plan. First, we use the values 80 grams and 50 grams after 10 years to calculate K. Then we derive the full decay formula and apply it to estimate future masses, like at 25 years. We also solve inequalities to find the time it takes for the mass to fall below 10 grams. Finally, we discuss real-world applications of this model, such as carbon dating, radiation therapy, and nuclear waste management. This concludes the summary of our Pbl table on radioactive decay. Thank you. Hello everyone. I will now present the Pbl table based on Newton's law of cooling. Let's start with the facts. An object is removed from a furnace at 1500 Fahrenheit and the surrounding or ambient temperature is 80 Fahrenheit. After 1 hour, the object's temperature drops to 1120 Fahrenheit. And we know the cooling follows an exponential decay model. This is a heat transfer problem between the object and its environment. Moving to the ideas. We apply Newton's law of cooling given by the formula T equals to A plus in bracket T initial minus with A in bracket E to the power of E negative KT, where A is ambient temperature, T is the initial temperature, and K is the cooling constant. Using the known data, we can calculate K and then apply the model to find the object's temperature at 5 hours. We can also graph the decay to understand how heat is transferred over time. Next, the learning issues, we need to know how to apply Newton's law of cooling to real-world situations and how to use logarithms to solve for K. It's also important to understand how temperature decay works over time and the difference between exponential and linear cooling. Finally, let's discuss the action plan. We start by identifying the known values. A equals to 80 Fahrenheit, T initial equals to 1500 Fahrenheit, and T1 equals to 1120 Fahrenheit. We plug this into the formula to calculate the constant K. Once K is found, we use the model to calculate the temperature after 5 hours. Then we verify if our results make sense by checking if the temperature approaches the ambient 80 Fahrenheit. Lastly, we connect the outcome to real-world applications like metal cooling industries and discuss how Newton's law is used in engineering to manage heat transfer efficiently. Thank you.
Soalan pertama, dia minta hasilkan mathematical formula. Jadi, menggunakan formula yang telah dia bagi, NT sama dengan NO, E kuasa negatif R, T, kita akan substitute informasi-informasi yang telah dia berikan sebentar tadi. Jadi, 50 kita akan gantikan dengan NT, 80 sebagai initial mass, dan E negatif R 10. Lepas tu, kita akan pindahkan 80 ke sebelah kiri untuk dibahagikan dengan 50 dan akan menghasilkan 0.625 sama dengan E negatif R10. Kedua-duanya kita akan darabkan dengan ln. Jadi ia akan menghasilkan ln 0.625 sama dengan negatif 10R ln E. ln 0.625 kita akan bahagikan dengan negatif 10 untuk mendapatkan R. Jadi R yang kita peroleh adalah 0.047. Dan mathematical formula yang kita dapat adalah NT sama dengan 80E kuasa negatif 0.047T. Okey, sekarang kita akan cari mass after 25 years. Maksudnya T akan digantikan dengan 25. Jadi seperti equation yang telah kita buat di sebelah, substitute 25 ke dalam T dan kita akan mendapatkan hasil 24.72 gram. Okey, soalan ketiga dia minta time when mass drop below 10. Jadi first kita akan tulis semula equation tu. NT sama dengan 80 E kuasa negatif 0.047T yang mana lebih kecil daripada 10. Jadi kita akan pindahkan 80 tu kepada sebelah kanan yang mana ada 10 tadi. Jadi kita akan dapat E kuasa negatif 0.047T lebih kecil daripada 10 bahagi 80 yang mana 10 bahagi 80 menghasilkan 0.125. Jadi kedua-dua belah ni kita akan darabkan dengan ln. Selepas didarabkan dengan ln pada kedua-dua belah, kita akan dapat negatif 0.047T lebih kecil daripada negatif 2.079 yang mana negatif 0.047 kita akan pindahkan ke sebelah kanan akan dibahagi dengan negatif 2.079. Maka T kita adalah lebih kecil daripada 44.23 tahun. Okey, untuk soalan sebelum B berkaitan dengan Newton's Law of Cooling. Informasi yang kita dapat adalah temperature at any time TT, proportional constant K, time in hours T, temperature of the environment TE yang telah diberikan adalah 80 Fahrenheit dan initial temperature kita TO 1500 Fahrenheit. Dan equation adalah TT sama dengan TE plus dalam kurungan TO tolak TE tutup kurungan E kuasa negatif K T. Okey, untuk soalan sebelum B dia minta cari core temperature after 5 hours removed from the furnace. Jadi diberi 1 jam adalah 1120. Jadi kita akan substitute 1120 ni ke dalam equation. Jadi 1120 Fahrenheit sama dengan 80 tambah buka kurungan 1500 tolak 80 tutup kurungan E kuasa negatif K 1. Jadi kita akan bahagikan 1120 tolak 80 akan bahagikan dengan 1500 tolak 80 yang menghasilkan 0.7324 sama dengan E kuasa negatif K. Jadi kedua-dua belah ini kita akan darabkan dengan ln. ln 0.7324 akan menghasilkan negatif 0.311 sama dengan negatif K ln E. Maksudnya 0.311 sama dengan K. Okey, selepas dapat K, kita akan masukkan 5 ke dalam T sebab dia minta 5 jam kan. Okey, jadi T5 sama dengan 80 tambah dalam kurungan 1500 tolak 80 tutup kurungan I kuasa negatif 0.311 darab 5 yang mana menghasilkan 379.89 darjah Fahrenheit.
Next, for discussion and conclusion. In part A, we studied radioactive decay using the exponential model. Starting with 80 grams, only 50 grams remain after 10 years. From this, we calculate the decay constant as 0.047 and predict 24.72 grams will remain after 25 years. The material dropped below 10 grams in about 44.23 years. This shows how radioactive substance decay quickly at first, then slow over time. In part B, we applied Newton's law of cooling. An object cooled from 1,500 Fahrenheit to 1,120 Fahrenheit in 1 hour. Given a cooling constant of 0.311, after 5 hours, the temperature was around 318 Fahrenheit. This proved that cooling is faster when the temperature difference is larger, which is key in thermal engineering and heat transfer design. In conclusion, both parts demonstrate how exponential function can model real-world change over time, radioactive decay, and thermal cooling. These models are valuable for predicting behavior and supporting decisions in science and engineering.